Hello everyone, this is your chapter 6 homework. I'm going to go ahead and make a video as to explain you how the problems need to be solved. I know I have posted the handout explaining the solutions, but if you need a little bit more information as to how to work out those problems, this video will be helpful to you. Okay. First one, system receives 575 of heat, joules of heat and delivers 425 joule of work. Calculate the change in the internal energy delta E of the system. So for this problem, we're going to be using equation delta E equals Q plus W. Q is the heat, W is the work. And then the heat is given by here 575 joules. It says a system receives. If the system is receiving, it is adding energy to the system. So that is going to be a positive value. So Q is positive, so 575. And then it says, and delivers 425 joule of work. If the system is delivering work, meaning the system is losing that amount of energy. So that's going to be a negative number. So plus negative 425 joule. So when you add these two together, will give you the correct answer, which is going to be 150 joules. Okay. And for the second one, it says system delivers 225 joule of heat. So the system delivers. If the system is doing something, is it going to gain that amount or is it going to lose that amount? It's going to lose, right? So it is heat. That means heat Q term is going to be negative 225. So then your delta E going to be negative 225 plus the work while delivering 645 joule of work. By delivering something, are we gaining energy to the system or losing energy? If you deliver, the system is losing energy, meaning your work also going to be negative. So negative 645. So when you add these two together, will give you the internal energy delta E of the system. Both are going to be negative terms, so your answer will be negative when you add the two together. Okay, that's how you would do your first two questions. And then the third question, system expands from a volume of 1 liter to 2 liter against a constant external pressure of 1 atm. The work done by the system in joule is what? So we want to find out the work, and for this question we're going to be using the equation W equals negative P delta V. Pressure indicated by P and delta V is the volume change. Final minus initial volume. From 1 liter to 2 liter. So then 2 minus 1 would be 1 liter. Right? And then the pressure is 1 atm. So 1 atm times 1 to 2, 2 minus 1, that would be 1 liter. So 1 atm times 1 liter will give you the answer as 1 atm liters. Now it's negative, right? So in your question, it is asking the work done by the system in joules. Now the question itself telling you the work has been done. So because of that, the answers are all given in positive terms. If it is just asked what is the work, or like the fourth problem, it is asking the value of W in joules. If it says the value of W in joules, then it can give you positive and negative values. But here it is telling you in words the work done by the system. That means it has to be negative if the work is done by the system. So that is why you don't see the negative sign in any of the choices. Okay. And we have 1 atm. But what we need to do is we need to convert it into joules. That's what we want it in the units. So how do we convert ATM liters to units? You were given the conversion in your lectures. 1 ATM atmosphere liters equal to 101.3 joules. Okay, 101.3 joules. So when you multiply this one, it's going to be 101.3. ATM liters cancel. 101.01 into 10 to the power 2 in scientific notation. 1.01 into 10 to the power 2 joules. Okay, that's how you would now do number 3. The answer is not none of these choices are correct. There is a choice that's 1.01 into 10 to the power 2. The negative sign is not given because the question is asking the work done by the system. Now the next question. Again, we're going to be using the same equation. System contracts from initial volume 15 to final volume 10. So then the delta V is going to be 10 minus 15. It goes from 15 to final 10. So the final volume is 10 minus the initial 10 minus 15. There would be negative 5 liters. Okay. And it's asking value of W. It doesn't say whether the work is done or work is done by the system or the surrounding has done the work on the system. So we have to give it with the proper sign. So W equals negative P delta V, and then the pressure is 0.800, and then the delta V is going to be 5.0 liters, and this is ATM. Okay, and this is going to be 0.800 times 5, going to be 4. 3 significant figures, 2 significant figures. We're going to keep the answer in 2. 4.0 ATM liters. But we need to convert this into joules. How do you convert it to joules? Remember, we have a negative sign right there. We have to carry that negative sign. 4.0 ATM liters. And ATM liters equals 101.3 joules. So 4 times 101.3, and you have to represent it with the proper sign. Okay, so you will find the answer for that. And number 5. A Snickers candy bar contains 280 calories, of which the fat content account for 120 calories. What is the energy of the fat content in kilojoules? So we were given 120 calories. So this is how you're going to perform this calculation. We want to find out what is the energy of the fat content in kilojoules. So we are going to convert calories to kilojoules. So you start with 120. Big number, calories. 120 calories. Okay. And then how do you convert it to small calories unit? 1 big calorie, calorie. Okay. Calorie equals 1000 calories. Calories. I'm just gonna write the shortened form cals. And then we can convert calories, small calories to kilojoules. And we know 1 calorie, this is small, calorie equals 4.184 joules. The answers choices are given in kilojoules. So 1000 joules equals 1 kilojoule. The reason here 1 calorie, you cannot just convert this 120 calorie saying that 1 calorie equals 4.184 because this is big calorie with the big C. But then you have to convert it, how many small calories are there for 1 big calorie. So 1 big calorie is 1000 small calories, and the conversion come from the small calories to joules. 1 calorie equals 4.184. So when you do this conversion, you will get the energy of the fat content in kilojoules. Okay. Alright, I'm going to erase this part now so I can get some space to do number 6. Calculate Q when 28.6 gram of water is heated from 22 degrees Celsius to 78.3 degrees Celsius. Now we want to calculate Q. So for this one, we're going to use Q equals mc delta T. And the mass of the water 28.6 grams. C is a specific heat of water 4.184 joules, and the units are grams per Celsius, and delta T is going to be 78.3 minus 22. Okay, so how much is 78.3 minus 22? Must be an easy calculation, but I want to make sure I do get the correct answer. 56.3 Celsius. Celsius to Celsius get cancelled. Grams to grams get cancelled. And then you can calculate the rest. And this will be given in joules. What you need to do is you need the conversion. 1000 joules equals 1 kilojoule. Okay. So you can do your calculation like that. Okie doke. Next one. Number 7. Ethylene glycol. Alright. It has a heat capacity 2.42. We want to calculate Q. When 3.65 kilogram of ethylene glycol is cooled from 132 to 85 degrees Celsius. Again, we're going to be using the same equation like before. Q equals mc delta T, and your mass is going to be 3.65, and it's kilogram. It's given in kilograms, and your heat capacity is given in joules, grams per Kelvin. Well, we're going to keep it in kilojoules at the end. Maybe we can just leave it like that, or we can go ahead and convert it to grams. 1 kilogram equals 10 to the power 3 grams. Specific heat 2.42 joules, grams per Kelvin. And then cool from 132 to 85. So what is the final temperature then? 85, right? Times 85 minus 132. And this number is given in Celsius. But if you do a subtraction with either converting to Kelvin or keeping in Celsius, the value is going to be the same in a subtraction and an addition. So because of that, you don't need to convert Celsius to Kelvin when you subtract a value. Okay, but if you do have a division or a multiplication that involves Celsius and Kelvin, you have to convert Celsius to Kelvin. Okay, this is just a subtractions. 85 Celsius minus 132 Celsius is same as when you convert 85 and 132 to Kelvin and do the subtraction. Okay, and then at the very end you will be needing to convert it to kilojoules. For what you get from the previous one, you're going to be doing your conversion joules are there. So 1000 joules equals 1 kilojoule. Okay, that's how you would do your conversion. And then the answer is going to be negative. Why? Because the delta T right here, this term would be negative. So as a result, you will get a negative value. Okay. The next question. 1 gram piece of copper initially at 100 degrees Celsius dropped into a coffee cup calorimeter containing 50 gram of water at a temperature of 20 degrees Celsius. After stirring, the final temperature of the both copper and water is 25 degrees Celsius. Assuming no heat losses and that the specific heat capacity of water 4.18, what is the heat capacity of the copper in joules per Kelvin? Now, what's happening here is you have a coffee cup calorimeter, which is basically a styrofoam cup. And then it already has 50 gram of water. And the temperature of the water is 20 degrees Celsius. Okay. And after stirring the, okay, so you are putting a 1 gram of copper metal into the water. And the temperature of the copper is 100 degrees Celsius before you put into the water. Now water is at 20 degrees Celsius. When you put the metal that is hot as 100 degrees Celsius, what's going to happen to the water? Water will start heating up because you add 100 degrees Celsius water. So the heat goes outside the metal into the water. So then the temperature of the water will increase, and you can put the thermometer and you measure the temperature. And that is going to be now 25 degrees Celsius. When the water becomes 25 degrees Celsius and it doesn't change anymore, what would be the temperature of the metal going to be? Metal also going to have the same temperature because whatever the heat that metal had now released to the water. Temperature of the water will also be now the temperature of the metal. So we say metal and the water are at thermal equilibrium at that point. So at that point we can say the heat lost from the metal equals heat gained by the water. For water, heat gained. So that's a positive term for water. Metal was at a higher temperature. It lost its heat to the water. So that's going to be a negative term for the metal. But the heat, the quantity of the heat are the same amount. The only difference is metal lost it and then the water gained it. And we know that Q is represented by mc delta T. So if you can find out what is the mc delta T values for the metal and mc delta T values for the water, we can compare them, we can make them equal, and we can find out the heat capacity of the copper metal. Okay, so if you do like this, metal heat capacity of the metal times the heat capacity of the copper metal times the delta T for the metal equals the mass of the water times the heat capacity for the water times the delta T for the water. Right, because that represents Q. Only the difference is this is going to be negative and then the other side going to be positive. Okay. But what we want to find out is this guy, Cm. So then the metal capacity, not metal capacity, heat capacity for the metal would be Cm. Mass of the water, we were given the mass of the water 50 grams. 50.0 grams. Excuse me. 50.0 grams. And then the specific heat capacity for the water, 4.18 joules grams per Kelvin. And then the delta T. Delta T, now remember the final temperature for the water and the metal both 25. Initial temperature of the water 20. So 25 minus 20 is 5 times 5. Remember the subtraction of Celsius same as the Kelvin, so you can just say 5K. And you divide it by, remember we have a negative term here, you can keep it there. Mass of the metal, which is 1 gram, times the delta T. Delta T for the metal is final temperature 25 minus the metal was at 100 degrees Celsius to begin with. Okay, so 25 minus 100 is 75, negative 75. And that negative and this negative sign at the front get cancelled. So you will have a positive value for the specific heat capacity for the copper metal. So basically you can multiply 50 times 4.184 times 5 Kelvin over 1 times 75. I'm looking at the paper that I posted with the worked out answers. There I have done a mistake, 25 minus 100. I have put it as 25 minus 100, but it should be 25 minus 20. Okay, there is a little mistake for the delta T for the water. It should be, what I have shown here is correct, but in the one that I have posted on blackboard, I have put the delta T for water as 25 minus 100. Okay, so that's a typo. That's not correct. It has to be 25 minus 20, which is 5. And then the bottom one, 25 minus 100, is correct. Okay, sorry about that. I just noticed it right now. And that's how you would calculate the specific heat capacity for water. Okay. Okay, the next one, number 9. Sand is converted to pure silicon in 3-step process. The third step is SiCl4 plus 2 magnesium, giving you magnesium chloride and silicon, and the delta H is given. What is the energy change when 25 moles of silicon tetrachloride is converted to elemental silicon? How do we perform this calculation? Let's see. So SiCl4 plus 2 mg magnesium chloride plus silicon. And for this one, delta H is given as negative 625. We are asking when 25 moles of silicon tetrachloride, when you have 25 moles, what would be the enthalpy change? Okay, so we're going to use enthalpy and the number of moles in as our conversion. Okay, so to find out for 25 moles, we use the conversion, and according to the balanced equation, 1 mole of silicon chloride, when it reacts, silicon tetrachloride, when it react with magnesium, it gives out negative 625.6 kilojoules. Right? So the conversion is when you have 1 mole silicon tetrachloride, SiCl4, it gives out negative 625.6 kilojoules. So moles to moles cancel, so 25 times negative 625 kilojoules. That will give you the answer. And then the next one, number 10. Calcium hydroxide react with carbon dioxide to form calcium carbonate, used in ancient Romans. The reaction for this process is given. What is the enthalpy change if 3.8 moles of calcium carbonate is formed? Now let's look at if the reaction given is balanced. We have one calcium, one carbon, and then we have four oxygens. It's balanced. So according to the balanced equation, it's asking about calcium carbonate. So you locate calcium carbonate and there is 1 mole here. When 1 mole of calcium carbonate, it's giving 69.1 kilojoules. So when you have 3.8 moles, you use the conversion. 1 mole calcium carbonate gives us 69.1 kilojoule. And for 3 moles, you're going to multiply it by 3.8 to find out the enthalpy change. Okay. That's how you would do that. And number 11. Galena is the ore from which elemental lead is extracted. In the first step of the extraction process, galena is heated in air to form lead oxide. What mass of galena is converted to lead oxide if 975 kilojoule of heat are liberated? Okay. And again we are given the balanced equation. We want to find out what mass of galena is the ore from which elemental lead is extracted. Extraction process is heated to form lead oxide. So then your galena is lead sulfide. Okay. So it's asking what is the mass. So we're going to use the known one, negative 827.4 kilojoules liberated when 2 moles of lead sulfide is being heated. Okay, so that's the known one, but we're going to use this amount is what we want to find out. So 975 kilojoules. And then we're gonna compare this with the number of moles given, negative 827.4 kilojoules liberated when 2 moles lead sulfide heated. And then this is the number of moles. You're going to convert it to, if you have 1 mole lead sulfide, meaning that's going to be the molar mass of lead sulfide, which is 239.2 grams. So you start with what's been asked, 975 kilojoules. And then you're going to see it's negative 827.4 kilojoule is liberated when 2 moles lead sulfide is heated, and then converted to mass. 1 mole lead sulfide is the molar mass of lead sulfide. Check to see if this molar mass is correct. Okay. Yes. So this is already given the number as the negative. Heat is liberated. Again, that tells us it's an exothermic reaction. So your answer does not have to be in negative, because the question itself says heat is liberated. Okay. Okay, probably we have probably I can do everything in one video. Let's see. Number 12. Use Hess law to calculate the enthalpy change for the reaction. Tungsten oxide with hydrogen gas giving you tungsten and water. This is the reaction that you want to find out the enthalpy. But we are given this data tungsten plus 3 oxygen, giving you tungsten oxide, and delta H for that reaction given. Hydrogen plus oxygen, giving you water, enthalpy for that reaction given. So we're going to use these two equations to get to this equation. We may need to switch it, we may need to multiply it or divide it, but somehow when we add these two together, we should be able to get the target equation, which is this one. Okay, now let's see how we can do this one. This one, tungsten, is written as a reactant, but here tungsten is a product. Our goal is to get the target equation from the given two equations. So this equation, let's say this one is 1, this one is 2. So the first reaction needed to be reversed. If you reverse it, the value of the enthalpy going to change the sign. So let's reverse the first one. That will give you 2 WO3, giving you 2 tungsten plus 3 oxygen, but the sign going to change to plus 1685.4. The next one, we have hydrogen as a reactant and hydrogen as a reactant, water product, water product. So the second reaction, we can keep it like that. Okay, 2 hydrogen plus oxygen, giving you 2 water, negative 477.84. Now let's see. Here we have 2 hydrogen, but what we want is 3 hydrogen. Correct? And we want 1 tungsten, and here you have, so we need 1 tungsten, but here you have 2 tungsten. So what do we need to do? We need to divide this reaction, the first reaction, by 2. When you divide it by 2, that will make it WO3, giving you W plus 3/2 oxygen, dividing this by 2. So then what happened to the enthalpy amount? Enthalpy amount also need to divide by 2, and that will give you 1685.4 over 2, 842.7. Still it's a positive charge since we didn't reverse it. Now we have that. Do we need to do anything for the next reaction? Now for the reaction 2, we need to multiply it by 3/2 to match the target reaction. This one. Okay, we have to multiply it by 3/2. So that way, let's try to do that. Multiply this one by 3/2. When you do that, 2 hydrogens times 3/2, that will give you 3 hydrogen. The whole thing need to be multiplied, right? So that will give you 3 hydrogen plus 3/2 oxygen, and 3/2 water means 3 water, and negative 471.84 also need to multiply by 3/2. Okay, negative 471.84 times 3/2. That will give you 707.76. kilojoules. Okay. Now when we add these two, this equation and this equation together, are we getting our target equation? See, we had to manipulate these equations. So let's add those two that I circled in green. When you add the two together, it will give you WO3 plus hydrogen, 3 hydrogen, 3H2, giving you W plus here. What about oxygen? Here's oxygen, 3/2 oxygen. Reactant, here it is a product. So they both gonna get cancelled. So we don't have to include them. Plus 3 water. I have written this information in our handout also that I posted, so you can refer to that. That one has no space there. So by looking at these two, did we get our target reaction, which is WO3 plus 3H2, W plus 3 water. Very good. So we got our target equation. So accordingly, we have to add the enthalpy values, which is 842.7 minus 707.76. Eight 42.7 134. What did I do wrong? Didn't get it. Eight 42. Let's do it again. 842.7 minus, what did I get doing that calculation? Let's try it again. 471.84. 471.84 times 3/2. 707. 471. No, 477. I have done a little mistake. That's why. Okay, I have written this number different. 477 over here. I have done a little mistake by when I'm writing the amount. 477. That's why. 477.84. So 477, it should be 477.84. So 477.84 times 3/2, 716.16. That makes sense. 716. This number need to change. 716.76. 716. 76. So now 842.7. Yes, 125. Wonderful. 125.9. So we have that answer there. Yes, 125.94. So that's how you would do this calculation. Okay. Number 13. I'm going to erase now all these things. Number 13. Which one of the following is not a correct formation reaction? Products are not correct. Which one of the following is not a correct formation reaction? Products are correct. Okay, products are correct. Formation reaction means when you are making something, it has to come from its elemental form and how these elements exist in nature. Meaning carbon exists in nature as graphite. Hydrogen exists in nature as hydrogen gas, not hydrogen atom. Oxygen doesn't exist in nature as O, it exists as O2. So if you want to represent 2 oxygen, you cannot represent it like this, O2 hydrogen like that. It has to be H2 like this. Okay? But you can put a coefficient over here at the front. So it has to be written in elemental form in your reactants. Now the first one, carbon graphite to carbon diamond. Asking not correct. So this correct, the first one. Carbon graphite and carbon giving you diamond from the carbon graphite. And then the second one, you have a half hydrogen. Hydrogen is written correct. Chlorine exists in nature as Cl2, written correct. And giving you hydrochloric acid gas. So the both hydrogen and chlorine are gases, but in HCl, when you take hydrogen chloride, there is one hydrogen, one chlorine. So your stoichiometric ratio should be equal. So half hydrogen, H2, means hydrogen represent 1 there. So it has to be half hydrogen. So the second one also the same, and chlorine also the same. The third one, 6 carbon graphite and 3 hydrogen, C6H6. It's an organic compound called benzene. We need 6 carbon, it comes from 6 graphite. 6 hydrogen, they have to come from H2, hydrogen gas, 3 hydrogen gases. 3 times 2, that's correct 2. And D, 6, we want to form glucose, C6H12O6. Carbon comes as graphite, 6 carbon, 12 hydrogen. That 12 hydrogen comes as 6H2, which is correct also. Oxygen exists in nature as O2, and if you want to have 6, it has to be 3 times 2, 6 oxygen. So that is correct too. The last one, we are making water. Hydrogen, we need 2 hydrogens as H2. And here oxygen is represented as atomic oxygen, just O. But that's not how oxygen exists in nature as O2. But since you have 1 oxygen here, to represent it as 1, you have to do it half oxygen. So this is the one that's not correct. Okay. Number 14, also the same. Which one of the following is a correct formation reaction? Let's see, C6H12O6, 6 carbon. Here 6 water is given. That's not correct. It has to separate into hydrogen and oxygen. We are making CH4. Carbon graphite is written correct, but the hydrogen doesn't exist as hydrogen H. It has to be H2. So to represent 2, it should be written as 2H2. So that's not correct either for hydrogen. This one, there are 2 carbons. That's correct. There are 5 plus 1, 6 hydrogen. So 3 hydrogen, that's written correct. 3 times 2. And 1 oxygen, half oxygen. So that's correct. And then the carbon diamond going to carbon graphite. That's also correct. Diamond can become graphite with the time. And then it's asking for a correct formation reaction. Well, graphite doesn't form from the carbon, diamond. Diamond is being formed from graphite. So that's not correct either. And then the last one, water. There are 2 hydrogens, so H2. Oxygen has to be written as half oxygen. So this is also not correct. This is also not correct. So the correct one is C. Okay. 15. Calculate the delta H reaction for the decomposition of calcium carbonate to calcium oxide and carbon dioxide. And we are given the formation values. So delta H for the reaction, we use sum of the delta H values for the products minus the sum of the delta H values for the reactants. And what are our products? This is our equation. Calcium oxide, carbon dioxide. Our reactants are calcium carbonate. So the delta H values for the product, calcium oxide, here. And it has 1 mole, negative 635.1 kilojoules per moles, plus the other one, carbon dioxide negative 393.5. so that is the sum of the product. You add these two together and you subtract the formation of calcium carbonate, which is negative 1206.9. okay, and all of these are in kilojoules per mole. So add these two together, negative 635.1, negative 393.5, and this negative will make it positive. So you can find the answer. Let's see. .1 plus 393.5. Those are going to be all negative. 1028.6. okay. .128.6, and then you have a negative term. Negative will make it positive, 1206.9. That will give you the answer in kilojoules per moles. And then the next one, 16. Calculate the delta H for the reaction. Okay, same thing like number 15. We are given the balanced equation along with their delta H values. Again, the delta H for the reaction is going to be sum of all the delta H values for the products minus the sum of all the delta H values for the reactants. And our products are going to be these two. SiCl4 delta H formation, negative 657.0. All of these are in kilojoules. That's your product. Plus another product is water. So water value is here, negative 241.8, and there are 2 water molecules, so you have to multiply it by 2 since there are 2 water molecules. Okay, and then that's the products minus the reactants. SiO2 is your reactant. HCl plus SiO2 right here, and then it has 1 mole, so negative 910.9 plus you have SiO2, we just got that one down, and 4HCl is one of your reactants. So HCl is negative 92.3, and there are 4 of those, so you have to multiply it by 4. So you take the answer here and then you subtract what you get from the reactants. And then the detailed numbers what you get from these calculations are also given in the handouts I posted. So that should give you the final answer for this one. Okay. All right then. That's all we have for this one.